Yes, so the next part is determination of spacing. Now, to calculate spacing, first we have to consider bar diameter. So let's use 8 mm, 8 mm diameter of the bar. Normally 8 mm diameter of the bar is sufficient for majority of the slabs. Okay, only if the span is more than 5 meter or 5.5 meter, or in one way slab when the span is more than 4.5 meter, then we may have to use 8 mm diameter bar. But obviously for small to moderate spans, 8 mm diameter is more than sufficient. So along short span, we'll calculate area or the spacing of the reinforcement. So simple equation we need to remember, that is A5 upon AST. So what is A5? A5 is area of one bar, cross sectional area of one bar. So for 8 mm diameter, cross sectional area is 50.26. Okay. So we are getting here spacing as 179. Now here one thing is important, that is B. Why B is 1000? Because already we have considered a strip of 1 meter width while calculating area of steel as well as bending moment. So here spacing also we are getting in a meter. Okay, so that's why this is 179.5 mm. One check is important here, and that check is given in IS code. Okay, so here what is that check? That maximum spacing shall not be more than 3 times effective depth or 300 mm, which is less. Now dx is 181, so first value we are getting as 543 and second value is 300 mm. Whichever is less, that means 300 mm is less, but we are what is the spacing we are obtaining, that is less than 300, so we can use 179. So round up it to the lower side, we'll consider 170 mm. Okay, so hence here it is written provide hash at about 170 mm center to center. So also calculate AST provided, since we are not provided the same spacing 179. Okay, so little bit less spacing is provided, hence the area of steel will increase. So that increased area of steel is 296 mm square. Similar calculations will do for long span. So for a long span, the spacing we are getting as 173.31, and maximum spacing again here important is you need to write 3 times dy, that means effective depth along y direction into 3. So we are getting here also spacing as 170, that means along both directions we are getting spacing as 170. Calculate AST provided. Now check for deflection. Already we have uh, provided depth by using serviceability criteria initially. Okay, but there at that while using the modification factor, while calculating modification factor, we have assumed PT as 0.3%. Okay, but let's see whether that 0.3% is correct or not. So here ASTX provided is 296, so this check is to be provided along shorter span. So calculate PT. PT means percentage of steel in that cross section. Here ASTX provided divided by B into D suffix X. Okay, so effective depth is to be used. Okay, since we are using steel along X direction, this check is provided along short span. So obviously depth of short span bars is to be considered. We are getting that PT as 0.16%. Now this 0.16% is less than 0.3%. Okay, and here it is safe. Why is it safe? It is very simple logic. When we consider the diagram of modification factor, so let's go to figure number 4 once again. So here we have figure number 4. Yes. Now we have assumed point 3, which is somewhere here. Okay. Now when we are in the percentage of steel is less than 0.3, that means it is on this side. Okay, on the left hand side. It means on the left hand side the modification factor is on the higher side. So if the modification factor is on the higher side, obviously required depth is even less. Okay, that means the check which you have provided here, if PT is less than assume PT, then easily you can say that check for deflection is safe. Now distribution steel. In two-way slab, main steel is to be provided along both the directions in the middle strip. But what about eighth strip? So in the eighth strip, we can provide distribution steel. So let's use hash 8 bars and calculate spacing of distribution steel. So how much is the area of distribution steel? So it is 0.12%. Okay, it's same as that of AS minimum. So that value is coming as 240 mm square. Calculate the spacing with the same equation as that of main steel, and we are getting 117. Now for this also we have to provide the check. And what is that check? Check is for maximum spacing. So maximum spacing of distribution steel shall not be more than 5 times the depth or 450 mm, whichever is less. Okay, so already we are getting this value only 117. Okay, so we can provide that 117 is rounded to 110. So we are writing here provide has 6 about 110 mm center to center. Now next important reinforcement is torsion reinforcement. When we are using table number 26 to calculate bending moment, so it is assumed that your edges of the slab are held down. Okay, so when edges are held down and there is a need of torsion reinforcement. Okay, the provision of torsion reinforcement is mandated here. So when edges are held down and both the edges are discontinuous, then as per IS 456 we have to provide 3 by 4 ASTX. Okay, well, now this point is given just before table number 91. Already we have used table number 91 to calculate the bending moment. Okay, here, yes. So in here this is annexure D, and in that the details of torsion reinforcement are given here. Okay, well, now by using these clauses we are using this equation. AT is equal to 3 by 4 ASTX. Okay, now 0.75 of ASTX required, not provided, is required. Okay, at the corner at which both the edges are discontinuous. Okay, there is one more point which is given in IS code, that if only one edge is discontinuous and other is continuous, then this ratio is given as 3 by 8. That means 50% of this is to be provided as torsion reinforcement at that corner. So here we are getting area of torsion steel as 210 mm square. So let's use has 6 bars and calculate spacing. It is 130 mm. Now, as per IS4, it is clearly mentioned that this torsion steel is to be provided in the form of two meshes. One is at top and second one is at bottom for length LX by 5 along both the direction. Okay, so bars are orthogonal to each other. Now check for shear. Though majority of the slabs are always safe in shear, but still how to provide this check for shear, that we'll see. So here, since all the edges are discontinuous, okay, so obviously we'll consider at short edge both edges are discontinuous. So WU max, that means ultimate shear force at support. So it is given by WU into LX effective by 3. So that value is coming as 20.4. Okay, since alternate bars are bent up, so we have to consider tension steel, okay, which is half of the AST provided at midspan. So at midspan we have provided steel as 296 mm square, and you are getting here half of that as 148. So calculate PT, and PT is 0.085, which is very less, and for which the tau c value is 0.28. So tau UC value, which is to be taken from table number 19, page number 73 of IS 456, and K value is 1.2. Now this value, the K value depends on depth. So let's move to the table of shear reinforcement. Just a minute. Yes, so this is the table by using which we can calculate tau UC value. So here percentage of steel is given, and for different grades of concrete the values are given here. Okay, and the value of K, the K is given according to the depth. So if depth of the slab is 150 or less, K value is 1.3. Okay, and as depth of the slab increases to 300, K value decreases here. Okay, so this clause is utilized in this equation. Okay, so we got here tau UC as 0.28 and K value as 1.2. So let's calculate the shear carrying capacity of reinforced concrete section. Okay, so that is VUC. VUC is given by as K into tau UC into BD. D is again the small depth. Okay, when you are giving this check along X direction, so obviously we have to provide D for X direction. Now here tau UC into K into BD, so that value is coming as 58.128 kilonewton. Okay, since VUC is greater than VU max, it is safe. Similar type of calculation is necessary for longer edge. Okay, only the equation is different. Okay, it is WU max, okay, into W into LX effective into beta divided by 2 beta plus 1. Okay, and it is 20.47 kilonewton. Since alternate bars are bent up, again half the steel is considered. Okay, and this is also safe. Similar calculations are required. Only the equation of VU max that is different. Okay, well, all the steps are completed. Now let's discuss about the diagram. Now this is the cross section. Now in this cross section, alternate bars are bent up and along both direction hash at about 170 mm center to center spacing is provided. So here the bars which are provided at bottom a line, that is the short span bar, and which is bent up at distance L by 7. Okay, if it is long span or short span bar, L by 7 is to be considered. Okay, since the edge is discontinuous. The dots are the distribution. The distribution steel is provided in the edge strip, and the dots are it is the steel along longer direction. The thickness of the slab is shown here. Okay, and this is the reinforcement detailing of in plan. Now along both the direction, the spacing is same. So which is shown here. Only two bars are shown as a representative. Okay, well, so main steel is provided. Okay, and in the edge strip the distribution steel is provided. Okay, and already here written that distribution steel is provided as has 6 about, yeah, area has 6 about 110 mm center to center. Okay, that is the distribution steel is provided. Along with that, torsion steel is also provided. Okay, and these are the cyan color bars which are the torsion steel. Okay, and here distance is shown as Lx by 5. Well, so this is the diagram for two-way reinforcement. Okay, so this is the simplest design of two-way slab. Okay, in which all the four edges are discontinuous. If one edge or two edges are continuous, then obviously you have to consider adjoining slab while calculating the area of extra steel or requirement of extra steel at the support. Okay, so that we'll see in the further examples. Okay, so that's it for today. Thank you very much.